Hey, how's it going? Am I live? Let me look at my phone and double check. Hey, did I have music going last time? I thought I had the music set to not show up in the stream, but it looks like maybe I did have it set to go up in the stream. Sorry about that. YouTube on my phone. Hey, it says I'm live. Cool. Let's see, where were we? A couple points I should have hit last time that people asked about. Some 2.5 info. So, stuff from 2.5. Let me say this stuff real quick. So, here's an example that gets at what I want to say. At a production level of 375 units, marginal revenue is 8, and marginal cost is 6.8. If we're trying to maximize profit, should we increase or decrease production? So last time I sort of got hung up on the whole marginal profit equals marginal revenue minus marginal cost thing, which is like a perfect segue into chapter 3 because it leads to the first rule of derivatives, the adding subtracting rule that we don't really give the rule name to. But I should have talked about this thing. This is sort of one of these Goldilocks type situations I mentioned before, where what's going on here? The marginal revenue and the marginal cost are telling us how much will we bring in and how much will it cost to make one additional item. Or it's a derivative, which is a little more complicated idea than that, but when we're talking about margins, we usually think about it in those terms. This is saying the next item we make will bring in $8 and costs $6.80. Should we make it? If I'm trying to maximize profit, then yes, this will bring in more than it costs. So we should increase production. And in general, to maximize profit, we want to increase production if marginal cost is less than marginal revenue. We want to decrease production if marginal cost is bigger than marginal revenue. Remember, this is telling us that the next item we make costs more than it brings in, so it says we shouldn't make that item. But it's not just talking about the next item, like that's the way we think of it as our shorthand oversimplification, but it could just as easily be talking about the last item. When the next item costs more to make than it brings in, that is saying in the same way that the last item we just made cost more to make than it brought in, so we shouldn't have made it. We should decrease our production. And if marginal cost equals marginal revenue, so this is the baby bear situation where something is just right, then it is maybe maximized. We don't actually know that it's a maximum. The thing we can say is that if profit is maximized, then marginal cost must equal marginal revenue, because, like we said, we can improve our profit if it's one way or the other, by going one way or the other, depending on which one's higher. If they're equal, maybe we're already at the maximum. And this fact is sort of a cool trick to be able to do with a graph. Here's an example. Suppose I graph our revenue function. Revenue function is often a straight line. And I graph our cost function. And I want to be able to look at this graph and say, where is profit maximized? Let's add some tick marks down here. Let's call this 100, 2, 3, 4, 500, 6, 7, 8, 900. Well, what is profit? Profit is revenue minus cost. I want to know, when is the gap between revenue and cost at its biggest? At any given point, I can think about profit as how much is the distance between the current revenue and the current cost. And it's not just distance. I need the revenue to be bigger than the cost. Like here the distance is pretty big, but this is a place where the cost is bigger than revenue. This is a big negative profit. I don't want a big negative profit. I want a big positive profit. I can look at this picture and try and visualize a bunch of these vertical sticks and ask, I just restarted the computer hoping that would make this not happen. Hey, my picture's still here. When is profit maximized? Profit is revenue minus cost. I'm thinking about, when is this gap at its biggest? I can think about sliding this vertical line up and down and asking, when is this biggest? And I can get a pretty decent answer that it's somewhere around this area is where the profit is at its maximum. I can do way better than that, though, if I use this second way of thinking, that profit will be maximized when marginal cost equals marginal revenue. Instead of visualizing those vertical sticks that I don't actually see and are hard to compare against each other, I want to think about, when does marginal revenue equal marginal cost? Marginal revenue and marginal cost are derivatives, and if you hand me a graph, marginal revenue is this slope. Marginal cost will be this slope, which will be different as time goes by. In this context, and in many contexts, the marginal revenue has a constant slope. This is the situation where you assume the price is staying the same, no matter how many you make and sell. Which we often do. Like there are products where you can't really mess around with the price because there's other people selling the same product, and if you charge more than that, you'll be out of the market. The thing we're trying to visualize is profit will be maximized when marginal revenue equals marginal cost. So this slope is staying the same. Makes it pretty easy to compare. I'm looking for, on the cost curve, when does the slope match this slope? This slope is flatter than this slope, so I should move to the right. This slope is steeper than this slope, so I should move to the left. This is exactly what these concepts are telling us, that when the revenue graph is steeper than the cost graph, scooch to the left. If the cost graph is steeper than the revenue graph, scooch to the right. And things are going to be best when they're exactly even. Where are they exactly even? Looks to me like it's right about here. So, I lost my tick marks when the thing crashed. This will be the quantity that maximizes profit. There's this wording that's a little bit awkward. You want to talk about the maximum profit. This thing we're pointing at right here, though, isn't the maximum profit. The maximum profit is what is the profit at this point. The thing we're talking about is where is profit maximized. We're not saying what the biggest thing is. We're saying where to look for the biggest thing, and those are going to be two different things. This is like the x value, and the maximum profit is the y value. Usually once you have the x value that maximizes it, it's not hard to plug that into whatever you're dealing with to say this is what the maximum is. And often we won't say that as part of the answer. Like this question was asking where is profit maximized, not what is the maximum profit. Anyway, whatever that is on the X mark, this is a nice visualization thing. And the key thing is, like the reason I'm emphasizing that this is valuable is looking at these vertical lines and trying to estimate which one is biggest. Our eyeballs are generally not very good at that. Looking at this, though, this tangent line is a thing that human eyeballs are more accurate at. Sometimes with a graph you can just glance and know what's going on here. Anyway, that's the topic from 2.5 that I missed last lecture. Let's keep moving into 3.2, which is about derivatives of exponential functions. And logs. Let's write down three functions. Just like last time, I made some charts and said let's compute some derivatives, and pretended that I had a class full of students to compute those derivatives, but I just wrote them down. Oh, come on. My stylus is already dead for the first time today. I guess that makes sense. I didn't change it at the start of class. Working. Hooray. Okay. I'm going to write down three exponential functions. F of x is 2 to the x, g of x is 3 to the x, h of x is 4 to the x. Three different exponential growth functions. I put yours too high. And I want to compute the derivatives of each of these at a bunch of points. If I stick in 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, and I wanted to compute what is f prime of 1, I would probably do that by saying f of, I don't know, 1.01 minus f of 1 divided by 1.01 minus 1. And that top is 2 to the 1.01 minus 2 to the 1 divided by 0.01. And I get, dear calculator, oh, you went to sleep. Hey, you're back. What is 2 to the 1.01 minus 2 to the 1 I know is 2. Divide that by 0.01. I'm getting the number 1.39111. Round that to 1.39. This is worse than the last time. Last time we made this chart, everything turned out to be a whole number. In this version, basically nothing's going to turn out to be a whole number. So the goal is, again, if I had a room full of students, I'd say, hey, everybody grab one and compute it, and we'll fill out these charts, and we'll feel good that everybody in the room has got the hang of computing derivatives, and the numbers we'll get are 0.69, 2.77, 5.74, 1.09, 3.29, 9.89, 29.68. 1.39, 5.55, 22.20, 88.78. There's rounding error in all of these. I guess not just rounding error, but also the error that comes from not having the exact derivative, only from getting estimations. But our goal is to notice a pattern going on here, and hopefully we studied enough about exponential growth functions to know how they work, And the thing that makes a thing an exponential growth function is that at every step you are multiplying by the same amount. And in this case, if I look at consecutive numbers, this is about 0.7. Doubling 0.7 would be 1.4. Hey, double that is 1.4. Double that would be 2.8. Double that would be 5.6. They're a little bit off from, I had a room full of students who were rounding to different amounts and not all plugging in the exact same number. But if I get more and more accurate, it'll get more and more close to these things just doubling every time. And the fact that the original function was also an exponential growth function is sort of a suggestion that this is the right track. And sure enough, it is an exponential growth function. This function is some constant times a to the x. Here our a value is 2, and our some constant is going to be what is f prime of 0 is here 0.69. The number is not exactly 0.69, so this isn't really an exact formula for the derivative, but it's pretty good. We know it's an exponential growth function. We just don't know where is this first number coming from. If we knew this number, we would know how to work out all the others. It would be that times whatever power of 2. And the same thing's going on here. This is tripling at every step. And these numbers turn out to be quadrupling at every step. So these are also exponential growth functions. This one is going to be something times 3 to the x. And the something is the initial value is 1.09. This one was g prime of x, not f prime of x. And it looks like h prime of x is 1.39 times 4 to the x. So it looks like, and it is correct, that the derivative of an exponential growth function is an exponential growth function with the same growth factor, the same a value in its c times a to the x formula, but a different c value. And I guess our question is, where does that c value come from? And I'm going to get to what is that c value through the back door by noticing that, hey, multiplying something by 1.09 barely changes it. You're basically increasing it by 9% when you multiply it by 1.09. It looks like the derivative of 3 to the x is a little bigger than 3 to the x. His derivatives are numbers that are a little bit bigger than themselves. 3 to the 2 would be 9. This is a little bigger than 9. 3 to the 3 would be 27. This is a little bigger than 27. How much bigger? 9% bigger. And this is derivative is 2 to the x, but when you multiply by something by 0.69, it gets a little bit smaller. The derivative of 2 to the x is almost itself, but a little smaller. And for h, the derivative is itself but much bigger. So it seems like there's a continuous spectrum here, that for every number there is a constant out front that tells you what the derivative of that number to the x is. The derivative is itself but off by a little bit. And hey, somewhere between 2 gives you a function a little smaller than itself. 3 gives you a function a little bigger than itself. It would be reasonable to guess that somewhere between 2 and 3 is some number, call it a, where the derivative of a to the x is a to the x itself. Exactly. What would that number be? You can try 2.5 and then try 2.7 and get closer and closer. It turns out that that number is E. E is 2.7, 18, 28, 18, 28, ... If you ask your calculator for the digits, it'll show you this many. It looks like these 1828s might be repeating. It's not. That's a coincidence. It's sort of lucky that the calculator cuts it off there. This is like pi. It's an irrational number. It goes on forever without repeating. And it's one of those constants. And this is our first item to go in the list, is that the derivative of e to the x is e to the x. This is the function that is its own derivative, or one of the functions that is its own derivative. Remembering that e is something, and thinking about the things we did in an algebra class when we learned about e to the x, we learned about natural log. Once we get natural log on the brain, we have a shot of working out that natural log of 2 and natural log of 3 and natural log of 4 produce those numbers that we didn't know where they came from before. Natural log of 2 is 0.69. That's nice. Natural log of 3 is 1.09. I think that one rounds up, but those are the first digits. The natural log of 4 is 1.38. Hey, these are these numbers. And now I know how to take the derivative of anything to the x. The derivative of any number to the x. It wants to be like e to the x, which is its own derivative. E to the x is the easy version of this to remember. The way I'm remembering this is the derivative of a to the x, kind of like e to the x, wants to be its own derivative. It's not its own derivative, but it's only off by a constant. The constant that it's off by is natural log a. This feels like a gross hard formula. Most of the time, this formula is easier once you remember that ln of a is a constant. Constants don't usually make problems more difficult, or at least not calculus-type problems. Sticking a constant in front of a function doesn't make it harder to take the derivative of. The constant just hangs out there, and so on. The book will also use one more version of this formula that I think is kind of redundant, but I'll mention it here. That the derivative of e to the kx is k e to the kx. If you have a number up top with the x, then the derivative of e to the that number is itself. I don't like writing this out as a separate rule because it dumbly looks like it's frustrating how much this looks like the power rule without being the power rule. Remember, the power rule tells you the derivative of x to the n is nx to the n minus 1. And having the exponent fall down the way it does in the power rule, and also does in this e to the kx rule, to me is bad, because these are different rules. The key thing is this is stuff to the x. The power rule is for x to the stuff. Those are different rules. And the fact that both of them can involve a number falling down off of an exponent is kind of unfortunate. Like it just makes it harder to keep the two different rules straight. Let's do an example. If I write down h of x equals 14x squared minus 2x plus 3e to the x minus 7 times 4 to the x minus 11, let's find the third derivative of this function. So we're looking for triple prime. I want to take the derivative 3 times. Let's try it out. Start with the first derivative. 14x squared, this is the power rule. The 2 falls down on the 14. 14 times 2 is 28. My new power is 1. Derivative of 2x is the number 2. 3 is a constant out front, stays out front, and the derivative of e to the x is e to the x. So 3e to the x is also its own derivative. This one's rougher. 7 is a constant out front, stays out front. What's the derivative of 4 to the x? It's ln for 4 to the x. Minus what's the derivative of 11? It's 0. Okay, I didn't need to write that. There's the first derivative. Let's do it again. What's the second derivative? This is 28x. Derivative of 28x is 28. Minus derivative of 2 is 0. This goes away. Plus 3e to the x minus... Okay, 7 log 4, 4 to the x. Feels bad. Keep in mind, log 4 is also a constant. 7 log 4 is also a constant. 7 log 4, treat this all as a constant out front. The same way this 3e to the x had a 3 out front that stayed out front and we ignored it. We need 7 log 4 times, what's the derivative of 4 to the x? The derivative of 4 to the x is almost itself. It's 4 to the x, but I need to multiply by natural log 4. Okay, that means there's 2 natural log 4s out front now. Still just a constant out front. It's a different constant that now has 2 natural log 4s in its instruction instead of 2 of them. Ooh, I forgot. This is the second derivative. I should have put a second apostrophe here. Now let's take the third derivative. Derivative of 28 is 0. That goes away. I'm left with the 3e to the x minus 7. Derivative of 4 to the x will spit out another natural log 4. So now I have 3 natural log 4s on my 4 to the x. We got the third derivative. Let's throw one more function into the mix. So this is one more rule to box around. And this is one that you've already seen in the homework, if you've been doing the homework. There was a problem about, hey, look at natural log x and compute the derivative and see if you can figure out the formula. The formula for the derivative is... This is not how I've been writing these rules. The formula for the derivative of natural log x turns out to be 1 over x. It's a little bit surprising, because hey, wait a minute, 1 over x, I know how to take his derivative because he's a power. I thought the derivatives of the powers were all the powers. Weren't all the powers, when I took their derivatives, I got powers? Why has natural log also got a derivative of a power? Well, if I think about which power function would have given me x to the negative 1 as the derivative, I'm subtracting 1 from the exponent. Derivative of x to the 1/2 is 1/2 x to the negative 1/2. If my new exponent is 1 less than my old exponent, the thing that would have had a derivative of x to the negative 1 should have been x to the 0, and the derivative of x to the 0, this is 1, is 0 x to the negative 1, which is 0. So x to the negative 1 was missing from the list of derivatives that we produced from the product rule. And like that gap that we didn't notice wasn't there, it's filled by natural log. Natural log is the thing whose derivative is 1 over x. Some calculus books will have you learn the derivative of all different bases of logs. Ours doesn't. I like that. So let's mix that into an example. If I write down the function r of x is... Oh, let's do... 3 times 2 to the x minus 2 times x to the 3 plus x times 2 to the 3 minus, have I done all the permutations? 2 times 3 to the x plus 3 times x to the 2 minus x times 3 to the 2. So this is, I think, all ways of arranging 2, 3, and x in a something times something to the something. I'm trying to make this maximum confusing to make us maximum good at not getting confused. How do I take the derivative of this? Okay. What's the rule I'm using here? This is going to be an exponential function, because it's something to the x. Derivative of something to the x is itself with an extra natural log of that base. And the 3 out front is still out front. This is still a constant multiple of 2 to the x. The constant picks up a natural log 2 every time you take its derivative. minus, what's the derivative of 2 times x cubed? This is x to the stuff. This is the power rule. This is not the new one, this is the old one. The exponent falls out front. 3 times 2 is 6, x to the 2. X times 2 to the 3. What is going on here? This isn't x to the something, and it's not something to the x either. What? Oh wait, 2 to the 3, that's a number. I know that number. This is x times 8. That's 8x. Someone wrote 8x in a goofy way. That's just a constant multiple of x. The derivative of a constant multiple of x is that constant. That's not bad. Minus. This one's exponential again. Derivative of 3 to the x poops out a natural log 3. This one's the power rule. 2 falls down. 6x to the 1. This one is 9x. Derivative of 9x is just 9. There's the derivative. Depending on where the x is, it's a different rule. You got to get these rules straight. Here's an example trying to straighten out those differences. Yeah. Let's do this. If I write down u of x is e to the x minus natural log x, let's find the third derivative of this. Okay, we just take derivatives one at a time. Derivative of e to the x is e to the x. Derivative of natural log x is 1 over x. Now I want the second derivative. Derivative of e to the x is e to the x, minus the derivative of 1 over x. Oh crap, I need to rewrite this as a power. This is a place where I do a thought bubble to say, how would I have rewritten that? I would rewrite that as x to the negative 1. The derivative of x to the negative 1 is negative. X to the 1 less than that is negative 2. The minus that came down out front gets multiplied by the minus that's already there and is now positive. Third derivative. Derivative of that. E to the x, multiply that there, minus 2x to the negative 3. Boom. That's the third derivative. For natural log, you take its derivative once and it becomes a power function, and now you're using the power rule to take repeated derivatives. That's when you want repeated derivatives, which you don't usually want. A heads up, a big chunk of what's on this exam 1 is going to be taking derivatives of things. Here's a function, write down the derivative. By and large, I'm not going to be asking you to simplify those. So mostly, you don't need to worry too much about simplifying unless you have a reason to. Here, because I'm taking a derivative of a derivative, I have a good reason to simplify this, rewriting it as a power, because it's a thing I need to work with. If the problem just tells you to take the derivative, don't worry about trying to write that derivative in a simple way. So far, the things we write down aren't that gross. They're about to get worse, though. I owe you some more examples taking derivatives of exponentials and logs, but we're going to keep using them as we move forward with the bigger rules. Let's start talking about the bigger rules. 3.3 is the chain rule. And I'll say what the rule is. The rule is, this is like the less useful version of the rule first. The rule is the derivative of, the chain rule is how you take a derivative of a function of a function. So like, I know the derivative of x squared is 2x, but I don't know what the derivative of anything else squared is. This one I could do by foiling it out, but if I didn't want to foil it out, or if the power was bigger and I couldn't foil it out, or maybe if the power was a half, foiling doesn't make sense there. How do I use knowing what the derivative of x squared is to know what the derivative of other stuff squared is? The idea here is if you have a function of a function, what do you do? So that's what the chain rule says. The derivative of g of f of x is, you take the derivative of the outside function. You leave the inside of that outside function alone. And then you multiply by the derivative of the inside function. This is how the chain rule goes. This is the rule, but this is not usually the way I think is useful for learning the rule. What this is more like is a fancier, newer version of the old rules. Let's use this rule first. Let's take the derivative of 3x minus 1 squared. Let's do it twice, because I know how to do that without, and it's sort of, we can check our work. 3x minus 1 squared is, when I FOIL that out, 9x squared minus 3x plus 1 makes y equals 9x squared minus 6x plus 1. And now I can take the derivative of that. The derivative of 9x squared will be 18x minus 6 plus nothing, there's dy dx. How would I do this with the chain rule? This is something squared. I would be thinking to myself, I have something squared. The derivative of x squared is 2x. According to the chain rule, the derivative of stuff squared is going to be 2 times stuff times what's the derivative of the inside? The derivative of the outside function is doubling. I need to double the inside function. So double what? Double 3x minus 1. And then multiply that by the derivative of the inside. Our inside is 3x minus 1, doubling that. The derivative of that is 6. I get 2 times 3x minus 1 times 6. If I multiply this out, it does turn out to be 18x minus 6. It looks like the chain rule does work, but this is, I think, not a good way of thinking about the chain rule. Let me show you the more useful way of thinking about it. The more useful way is to think of it as a rewriting of all the rules you know. We know the power rule. The power rule says the derivative of x to the n, I'm going to use capital D for derivative here, is n times x to the n minus 1. We know the derivative of e to the x is e to the x. We know the derivative of something else to the x is natural log of the base times the something else to the x. We know the derivative of natural log x is 1 over x. These are the 4 things we know how to take the derivative of. 2 of them are specific functions, 2 of them are classes of functions. Well, the thing the chain rule does is it tells you how to take the derivative of not x to the n, but anything to the n. The derivative of stuff to the n is n times leave the stuff alone to the n minus 1 times what's the derivative of the inside. It's the derivative of, you take the derivative of the box, leaving the inside of the box alone, and multiply by the derivative of what's in the box. The derivative of e to the x is e to the x. I meant to say the derivative of e to the u, e to the something is, derivative of e to the something would be e to the something times derivative of the inside. What's the derivative of a to the stuff? Derivative of a to the x is ln a to the x. Derivative of a to the something is ln a to the something times the derivative of the inside. What's the derivative of natural log stuff? It's 1 over the stuff times the derivative of the inside. This is the one that people sometimes write a little bit differently, because like if you've got it 1 over something multiplied by something, it's sort of a waste of the top of the fraction. You could put the derivative on the top of the fraction, so sometimes people write this rule as du dx over u. It's the same thing, but like you're writing it as one thing instead of 2 things. This is the chain rule. Let's try it out. If I have y equals e to the x squared, this is e to the something. Derivative of e to the x is e to the x, so derivative of e to the stuff is e to the stuff times the derivative of the inside. What's the derivative of x squared? The derivative of x squared is 2x. If I have y equals 3x squared minus 2x plus 1 cubed, then the derivative of that is what? Derivative of x cubed would be 3x squared. The derivative of stuff cubed would be 3 stuff squared. It's 3 times something squared. It's going to be so tempting to write 6x minus 2 inside here, because I'm looking at that and I'm taking derivatives, and I know the derivative of 3x squared. But it is not time for that yet. I gotta hold on to my pants, leave the inside alone. We're going to take the derivative of that. The derivative comes out here. It's 3 times leave the inside alone squared times 6x minus 2. If it's not clear, let me say it one more time. The derivative is 3 times that stuff squared times 6x minus 2. If I have y equals, let's do a cube root. Cube root of e to the x minus natural log of x. Don't write y prime, this is y. This is the original problem. Y is this, so what's y prime? The derivative of this is, how do I take the derivative of that? First thing I want to do is remember I can rewrite that as an exponent. A cube root is a power of 1/3. This is stuff to the 1/3. What is the stuff that is being raised to the 1/3? It is e to the x minus natural log x. So to take the derivative, 1/3 falls out front. Subtract 1 from the exponent, that's the new exponent. What goes in here? We leave the inside alone. Don't do the derivative yet. And we multiply by the derivative on the outside. What's the derivative of the inside? The inside is e to the x. The derivative of that is e to the x. Minus, what's the derivative of natural log x? It is 1 over x. If I have y equals natural log of 1 plus 4x, how do I take the derivative of that? I don't know how useful this is. I usually have someone will have asked a question that'll have led me to start talking about, I think about a thing called my order of operations goggles. When you're trying to take the derivative of something, you need to be able to look at that and say, what is the outsidemost thing? If you had like one of those bad solar-powered calculators that you can only do one thing at a time, if I was plugging the number 3 into this, I would take 3 times 4, enter. And then I would take that number plus 1, enter. And then I would take the natural log, enter, and that would be my answer? My order of operations goggles are looking at that in those terms of, if I'm doing the computations one step at a time, what is the very last step? The very last step is this is natural log of something. I can look at this and say this is natural log of something. There's a 1 plus in there, but y doesn't equal 1 plus something. There's multiplication by 4 in there, but multiplication by 4 is like y doesn't equal 4 times something. There's more stuff after that. That's not the last button I will hit on the calculator that gives me my final answer. The last button I'm hitting is natural log, so that's the outsidemost rule. So that is the first rule I need to think about in terms of the chain rule. This is natural log of something. The derivative of natural log of something is 1 over. 1 over what? 1 over leave the inside alone, and then multiply by the derivative of the inside. The inside is 1 plus 4x. What's the derivative of 1 plus 4x? It is 4. There will be times where the chain rule sort of gets stuck in your brain and you use it when you don't have to. What's the derivative of natural log x? This is natural log of something. Derivative of 1 over... Derivative of natural log stuff should be 1 over stuff. What stuff? Leave the inside alone. Multiply by the derivative of the inside. The derivative of x is 1. You don't need the chain rule on this. This was the version of the thing we learned before the chain rule. The derivative of natural log x is 1 over x. The chain rule didn't lead us astray. We have 1 over x. We multiplied by an extra 1 that we didn't need to write there. But multiplying by 1 doesn't do anything, so, that's fine. When you are thinking in chain rule terms, you may find yourself writing a bunch of extra times 1's everywhere that aren't doing anything, and it's okay to put a bunch of times 1's. You can clean it up afterwards if it needs cleaning up. Many problems are just saying find the derivative and you don't have to clean them up. let's try y equals natural log of e to the x, and let's simplify our derivative this time. This is natural log of something. The derivative of natural log something is 1 over, leave the inside alone, times the derivative of the inside. What's the derivative of e to the x? The derivative of e to the x is e to the x. Wait a minute. This makes... Come on, wake up. Hey. This makes e to the x over e to the x. Which cancels and leaves 1. The derivative of this thing is 1? That's surprising. For a complicated function to have a derivative as simple as 1. Oh, wait a minute. Go back to your algebra class and remember, natural log and e to the cancel each other. Y equals ln e to the x, cancel, cancel, equals just x. And yes, the derivative of x should be 1. So, yes. A lot of the times, knowing derivative rules lets you confirm or re-notice or something. Like, these rules are kind of confirmed by calculus rules sometimes. Like, oh hey, it's sort of cute that because the chain rule spits out the derivative of the inside, and because x needs to not spit anything out, like, we have to be multiplying by 1 because we're multiplying by something, and the thing we multiply it by can't change anything because the derivative of natural log x needs to be the derivative of natural log x. So, yeah. Okay, let's see how bad this gets. So far, this hasn't gotten that bad. Let's write y equals... Ugh, I gotta change this battery again already. Not reasonable. Alright. The key thing about the chain rule is it's a meta rule. By which I mean, it tells me how to take the cube root of anything. I know how to take the derivative of cube root of anything if I know how to take the derivative of the inside. What if my inside is e to the 1 minus x squared minus natural log of 1 plus x squared? Okay, this is the cube root of something. My goggles look at this and say, this is the something to the 1/3, right? What that thing is doesn't matter. The chain rule works no matter what it is. We're going to need to take the derivative of that, and the time will come, but the chain rule only needs to happen one step at a time. This cube root is something to the 1/3. The derivative of something to the 1/3 is going to be 1/3 something to the negative 2/3. What goes inside here? Leave the inside alone. I know it looks terrible. Don't let that freak you out. We're just copying and pasting right now. Now I need to multiply by the derivative of the inside. Now is the place where I turn my attention. I avert my order of operations goggles to this thing. And I'm saying, now I need to multiply by the derivative of the inside. I'm basically starting from scratch on a new problem to ask, what is the derivative of this inside thing? And the way I start by answering the question, what is the derivative of this, is by using my order of operations goggles to say, what is the outsidemost thing of this? Well, the outsidemost thing is this is something minus something. And the minus rule, we don't really write down that much. We don't call it a rule, but it's, you leave the minus alone. I need the derivative of the first minus the derivative of the second. Okay, so now I need to turn my goggles to this. The derivative of that needs to go here. I need to know what's the derivative of this. The derivative of that's going to go here. When I look at this, I see this is e to this stuff. This is my green one. I look at the green one and say, you are e to the something. How do I take the derivative of e to the something? It is e to the, leave the inside alone, multiply by the derivative of the inside. Derivative of x squared is 2x. Minus, this one is natural log of something. How do I take the natural log of something? The derivative of natural log of something is 1 over, leave the inside alone, times the derivative of the inside. The 1 goes away, the derivative of x squared is 2x. I have written this very sloppily. Let me try writing this in a cleaner way. Like I'm doing all sorts of drawing to try and show off the things I'm thinking about. But the answer we should be writing down is 1/3 stuffed to the negative 2/3 e to the 1 minus x squared minus natural log 1 plus x squared times this thing was e to the 1 minus x squared times 2x minus this one was 1 over 1 plus x squared times 2x. I've got 2 mistakes here. Pause the video, see if you can see what mistakes I've got. I always want to take a second. I don't need to stop talking for you to pause the video. That's the point of saying pause the video. The first one is the chain rule wants us to multiply by the derivative of the inside is all one thing. Right now, the way I've got this written, this power is being multiplied by this and not multiplied by that. I need parentheses. That's the point I'm getting to. Mistake 1 is the chain rule has this is getting multiplied by all of the derivative. If the derivative is 2 parts, you need parentheses to group those together. Or in particular, if the derivative is 2 things added or subtracted, you got to wrap those in parentheses so it's all being multiplied. The second thing is the derivative of 1 minus x squared. I screwed that up. The 1 goes away, and the derivative of x squared is 2x, but the x squared has a minus on it. The derivative of negative x squared is negative 2x. A lot of students make this mistake. A way around this mistake is to write this is that stuff times 0 minus 2x. If I write the 0, I'm more likely to get myself to write the negative. The 0 doesn't matter, but as a trick for getting me to write the correct minus, it's pretty good. So, yeah, there's the derivative of this. That was a chain rule problem where in doing the chain rule we had to use the chain rule 2 more times. That's a thing that'll happen. Let's try stacking them like crazy. If I have y equals something to the 5th, what's being raised to the 5th? Natural log of something. Natural log of what? Natural log of something cubed. What's being cubed? E to the 2x squared minus 3. How do I take the derivative of this? My order of operations goggles tell me to start on the outside and work my way in. The outsidemost thing is this is something to the 5th. The derivative of something to the 5th is 5 something to the 4th. What goes inside? Leave the inside alone. And then multiply by the derivative of the inside outside. Now is the first place where I look what was being raised to the 5th and ask how do I take the derivative of that. When I look at this, I see it is natural log of something. The derivative of natural log of something is 1 over that thing. 1 over what? 1 over leave the inside alone. E to the 2x squared minus 3 cubed. Now is the time that I look at what was it we were taking the natural log of and try to write the derivative of that out here. What was inside that natural log? It was this. It was something cubed is the outsidemost thing now. My goggles look at that and see this is something cubed. Derivative of x cubed is 3x squared. Derivative of blah cubed will be 3 blah squared times the derivative of the inside. What is my stuff that's being squared here? It is e to the 2x squared minus 3. Now it's time to look at what was the thing that was being cubed and write its derivative down. The inside of the cube was this. This is e to the stuff. E to the something. Derivative of e to the something is e to the something. Derivative of e to the x is e to the x. Derivative of e to the stuff is e to the that stuff times the derivative of the inside. Now I'm looking at, man, I made this one deep. 2x squared minus 3. What's the derivative of 2x squared minus 3? It is 4x. Done. Box around it. I didn't use any parentheses because I didn't need to. It was just stuff times stuff times stuff times stuff. It's all grouped together. Multiplication doesn't care about the order. If I had a plus going on anywhere, that would need to get grouped into parentheses. I don't have that going anywhere here. This is the chain rule. The chain rule by itself is not that bad. The thing that makes it bad is the fact that the last step of the chain rule is what's the derivative of the inside, and taking that derivative of the inside could be as messy as a whole new problem. The chain rule is a problem that leads to a derivative of a new problem, which can be, you know, something pretty gross. The next section is 3.4. I want to do this out of order. I'm going to talk about 3.5 first, because 3.5 is a real simple one. It just gives us two more functions to throw into our list. The two new functions are trig functions. The derivative of sine x and the derivative of cosine x. This class doesn't have a trig prerequisite. You don't need to have used the functions sine x and cosine x before in your life. There's a lot of calculus you can do when you know the rules of trig and like things about sine and cosine. I'm not expecting you to know any of those things. As far as you need to know, sine and cosine are just buttons on your calculator. As long as you are set to radians, that's all you need to know. Be in radian mode if you ever need to plug a number into sine or cosine. Sine looks like this, by the way. Like, I guess I'll do a real quick note. Sine looks like this. Cosine looks like this. They are both the same wave kind of thing. The wave has a derivative that is increasing flat, decreasing flat, increasing flat, decreasing flat. So its derivative should be positive 0, negative 0, positive 0, negative 0, and it turns out that is exactly what cosine is. The derivative of sine is cosine. If I ask what the derivative of cosine should be, well, cosine is a thing that starts out flat, so its derivative should be 0, then it's decreasing, its derivative should be negative, then it's flat, so its derivative should be 0, then it's increasing, so its derivative should be negative. I get a thing that looks kind of like sine, except it's upside down. Sine starts out going positive, and the derivative of cosine starts out going negative. The moral of the story is the derivative of cosine is negative sine. We're grabbing these easy. We're grabbing 3.5 before 3.4 because it's really quick to say these two last rules of derivatives, and now I can start throwing sine and cosine into the mix with the other problems. So it will yeah, so we can keep drilling with these while we do the harder concepts. And just like the others, these have fancier chain rule versions. The derivative of sine x is cosine x, so the derivative of sine of something is cosine of that stuff times the derivative of the inside. The derivative of cosine of something is negative sine of that thing times the derivative of the inside. Let's try this out. Oh, heads up. One thing I meant to go back and mention that I didn't is I said there's this extra e to the kx rule. that you don't need to bother memorizing. And we're already past the point where you don't need to have memorized it, because derivative of this is e to the something. The derivative of e to the something is e to the leave the inside alone times the derivative of the inside is k. So chain rule has you covered. You don't need a separate thing to memorize for this e to the kx rule. But the book has it, so I'll mention it. Let's do a couple more chain rule problems with sine and cosine mixed in. If I write down y equals e to the x squared minus cosine x, how do I take the derivative of that? Order of operations goggles say the outsidemost thing is this is e to the something. Derivative of e to the something is e to the that thing times derivative of the inside. So I need e to the leave the inside alone times the derivative of the inside. Now I'm looking at x squared minus cosine x and saying, what's the derivative of that? Derivative of x squared is 2x minus the derivative of cosine is negative sine. Writing minus negative sine looks dumb. Minus a negative makes plus sine x. This needs parentheses because it's two things. Cool. I feel like these lectures are the places where being online is hurting my teaching the most, because I feel like I need to be looking at people and seeing how lost they are. This is really hard stuff to get. And like the hardest thing going on here is the fact that you just look at the problem and write down the answer. Some books work hard to figure out ways to break this down into more steps. I don't think those are good. I think what you need to be able to do is look at the function and write down the answer, and then maybe simplify it, but like all there is to this is keeping track of where I was. It can be easy to get lost. This sometimes feels like a choose your own adventure book where when you're reading it you say, I'm going to make this choice, but I'm going to keep my finger in the page to remember that I'm going to come back and try the other choice later, and then that stacks deeper and deeper, so now your fingers are all over the book trying to remember, okay, when I'm done with the pinky page I'm going to go back to the middle finger page. Like that's the thing that you need to do, is keep track of what you are doing. Let's do a couple more. If I hand you y equals cosine of 3x squared plus 1, what's the derivative of that? This is cosine of something. Derivative of cosine is negative sine. Negative sine of what? Negative sine of leave the inside alone. Multiply by the derivative of the inside. What's the derivative of the inside? It is 6x plus 0. Writing that plus 0 doesn't matter, but there are places where it'll stop you from making a mistake, so I'm going to write it often. If I have y equals sine 4x minus 6 to the 2x squared minus 11 natural log of 1 plus sine 3x. Let's take the derivative of that. What's the outsidemost thing going on? The outsidemost thing going on is I have something minus something minus something. Minus is the outsidemost rule according to the order of operations goggles. But the minus rule kind of doesn't matter. I don't have to remember any minus rule. It just means write the derivative of this minus derivative of this minus derivative of this. When you're first doing this, it might be helpful to like lay out your framework to say, okay, I'm going to write down something minus something minus something, and now I'm going to fill in those blanks. Like that can be a useful tool for saying, like, these are what the step for helping you keep track of what you need to come back to. The first blank needs to be what's the derivative of sine 4x. Well, this is sine of something. Derivative of sine of something is cosine. Cosine what? Cosine leave the inside alone. Multiply by the derivative of the inside on the outside. Minus this one is 6 to the something. What's the derivative of 6 to the x? It's natural log 6, 6 to the x. What's the derivative of 6 to the stuff? It's natural log of 6, 6 to the stuff. What stuff? The stuff is leave the inside alone. multiply by the derivative of the inside on the outside. Minus, what's the derivative of this? Like, the thing to keep in mind if you're getting lost is just, you can write this down as a separate problem on a separate sheet of paper and take the derivative of this and then say, okay, that's what's going into these blanks. Like, the only thing that's making these harder and harder is that you are inside of a problem when you do them. This is 11 is a constant out front, stays out front, times now what's the derivative of natural log? Derivative of natural log x is 1 over x. Derivative of natural log stuff is 1 over stuff. What stuff? Leave the inside alone. Times what's the derivative of the inside? Now I'm looking at this part, and that's derivative goes out here. Derivative of 1 is 0, plus derivative of sine stuff is cosine stuff. Leave the inside alone, multiply by the derivative on the outside. These rules stack on top of each other. If you're watching this lecture right now and you're completely lost, it helps to go back and do the easier homework assignments. Do 3.1, 3.2. Like, you really need to be at a place where you look at 3 to the x and know the derivative is 3 without thinking too hard. The end of the 3.1 homework, you should be close to that. That's it for 3.3. That's all you need to know for the chain rule. You're not really ready to do the 3.5 homework yet because it's going to have the 3.4 rules in there. Let's talk about the 3.4 rules. 3.4 is the last section we're going to cover before exam 1. Tomorrow will be review day. I might cover some of the... Actually, I might... Well, maybe I'll make videos for the next batch. I want to get ahead. I don't want to be waiting until Monday to cover the next bunch of stuff. But maybe don't watch... Well, I'll do review stuff tomorrow. I'll probably post a practice exam tonight and then cover it tomorrow. Crap, I'm supposed to not talk about classroom scheduling stuff because I want to be able to use this video for other classes. But that's probably what I'm going to do. 3.4 is about the product and quotient rules. The product rule is the rule for how to deal with multiplying things. We know how to deal with a constant out front. The derivative of 2 times 3 to the x, I know, is the 2 stays out front. What's the derivative of 3 to the x? ln 3 times 3 to the x. So I don't need a product rule if I have a constant being multiplied. But the thing I don't know how to do is what's the derivative of e to the x times sine x, for example. A function times a function. How do you do that? There's a cute visualization for the product rule. I don't know how valuable this is, but I'm too used to teaching this way to change. If the width of a rectangle is this, and the height of a rectangle is this, and they are both changing over time, the thing I want to think about is if the width of the rectangle changes a little bit, so I get a new slightly larger width, and the height of the rectangle changes a little bit, I get a new slightly larger height, how much has the total area of the rectangle changes? I'm using a rectangle because it gives me a reason to multiply two functions. And I don't really want to know what I want to think about is what is the new area? Like, how much does the area change by? That's the derivative, is what's the rate of change. Well, my original area was this. And my new area is going to be this. So if I'm asking about what is the rate of change of the area, I want to know what is my new area minus my old area, and then I want to divide that by the change in x, whatever that is. Well, the key thing to get is if I take the big rectangle and subtract out the little rectangle, what I'm left with is this rectangle, and this tiny little smaller rectangle. I get these three parts. What is the size of this rectangle? It is the width was f of x, and that got multiplied by this, which was the change in g. What is up with this rectangle? It's got a width of the old g of x and a width of what was the change in f. And then I got this tiny little rectangle, which it turns out is so small that it doesn't matter. We get that the change in area is about the change in f times g plus f times the change in g is the order we usually write these in. And if I divide all these by the change in x, these things become derivatives, and this is basically the way the product rule is usually written out. The product rule turns out to be, so here's the part to put in a box. The product rule says the derivative of a function times a function is derivative of the first times leave the second part alone plus leave the first part alone times derivative of the second part. Actually, you know what? I'm going to call today's lecture here. I've got the product rule written down with a bad justification for it, and we'll pick up from there next time. Try and get a look at 3.1 through 3.3 before next time, and we'll hit the product rule in more depth. I'll go over the practice exam so you know what to expect on the exam, and I'll talk to you tomorrow. See you tomorrow, guys.